So, hi everyone, welcome to this MIT and ESG seminar series. So today we are very honored to have Professor Baosen Zhang from the University of Washington, and I actually know him like about 8 years ago when we meet at Stanford University. We were talking about like tangent space of some non-convex optimization problem. And Baosen got his PhD from the University of Berkeley, and then after his postdoc, he joined the University of Washington. So today, Baosen will talk about safe and efficient reinforcement learning for energy systems. Okay, so now all's yours.
All right, thank you, Dale, for the invitations. Great to be here in person. See many old friends here. All right, so today I'll talk about sort of learning for energy systems, especially safe learning for energy systems. So this work on my students here. And really what, for people in this room, I guess listening in Zoom, as we all know that we have pretty ambitious goals about renewable integration. Many states are targeting, very large amount of renewable portfolio by 2050. People are trying to get to 100, so many states are trying to get to 100. So that to integrate this renewables, basically, we're going from a system that where we have little bit of renewables, a lot of traditional synchronous machines. We're going to a system where we have much more renewables that's connected by inverters. So through the talk, we'll sort of contrast between where you are generator dominant versus when you're inverter dominant. Right? So obviously, this system on the right is much cleaner, more sustainable than the system on the left. Right? We're replacing sort of carbon-intensive generation versus inverters. But the challenge is that being this is not very clean, although it is easier to control. So for this kind of conventional systems, you have about a few hundred generators you have to worry about. You have fairly large mechanical inertia. You have rotating inertia in the system. You don't have that many you have to think about. Whereas you move to an inverter dominant system, suddenly you're going from a few hundred generators to millions of things you have to think about. And each of them are much smaller. So at least from a control and stability point of view, it's quite a bit more challenging at this space. So the good thing about working with inverter dominant grid is that at least here, it gives you a lot of control capability. So inverters being power electronic devices gives us a lot of possibilities to control their behavior, whereas synchronous generation are typically much slower and there's not much you can do to control them. Inverters, there's a lot you can do to control them. So the idea, so for this talk, we'll focus on frequency response and think about how inverters should interface with the grid, what kind of control they should do. And we'll see how learning comes in. And so how do we do the right type of learning for this kind of systems? Right, okay, so frequency, what does frequency matter? Well, frequency is sort of the fundamental metric we look at in power systems. So this shows you a line outage in Florida that basically this one line trip causes huge frequency excursions all through the eastern seaboard, all through the eastern part of the US. So let me show this again. Right, so this is one line that trips somewhere in Florida. When you look at the frequency in the rest of the system, what do you see? This thing sort of propagates all throughout the US. And this leads to sort of a large tower loss, 2/3 of the state of Florida losing time. So we want to control frequency because we don't want this thing to happen. Right? You want to keep this frequency deviation relatively narrow. Okay. And so the way to do this is you want to adjust the power outputs of your inverters or your generators based on the frequency you measure in the grid. Okay. So, but once we have a lot of, so the interesting thing is once you start changing, going from conventional generation to say renewables, then what happens to see is you're starting to see more events, more low frequency events on the grid. So the one example of the Nordic system, they're starting to see a lot more events, right? As time goes on, as more things are displayed. And then if you read Firk's order basically says, well, if you're renewable, you must provide frequency response. Basically, if you want to integrate with the grid, you cannot just act like a load. You cannot act like a negative load. You have to participate in frequency response if you're a inverter-based device. So the question becomes, how should you participate? Right? What Firk tells you is you must provide it. Firk doesn't tell you how to do it. So we're interested in if your frequency, if you're inverter, how should you participate? So for traditional synchronous generators, this is not a big problem. You're sort of, yeah, okay, all right. Okay, so this is at least a problem that was well studied. And what they do is they follow negative linear feedback. Okay, what you do is you think of this generator, you measure your frequency deviation, you go through linear gain, and you adjust the power output according to the frequency you measure. And then what you basically you control all of this kind of linear slope. Right? You do a linear droop if you're a synchronous generator. Now, what do you do if you're an inverter? Okay? If you're an inverter, you don't have this kind of spinning machines anymore. What you do is you have electronics switching you at very high frequencies. And if you're told to respond, how should you respond? So whereas for conventional generator, you're quite limited in this control. For inverters, there's almost arbitrary choices you can do. You can measure frequency and respond in however way you want to respond. Okay, so this is now a design problem of what response you should put here. And so far, until now, as what we've been doing is we look at this thing and say, well, we know how synchronous generators work, so let's just mimic a synchronous generator. Right? So I can do anything I want. How about I mimic a synchronous generator? Well, is that optimal? Right? Can we do better? This is as if you have a smartphone. You're being asked, what do you want to do? You say, I just want to make calls. Right? So if you have this sort of design capability, can you do something that's better than a synchronous generator? Right? So that's our question. I don't know what curve I should have here. So I can do a linear curve, but maybe I can do some other curve that's slightly better. That has a better performance. Right? So one thing to remember is anything you design, the inverters have to play nice with synchronous machines. Okay, you cannot assume your system will suddenly go from no renewables to 100% renewables. Right? So we have to go through the phase where both significant. So what happens is you must, right? So it turns out if you assume everything is inverters, so it's easy to control. Because you don't have to, or at least relatively easy to control because you have full design capability. So here, what we want to do is we want the inverters to play nice. Okay, you still have synchronous machines. You have to respect their dynamics. At the same time, you want to design your own, to control your own feedback to be more optimal in this sort of mixed system. When we talk about systems, think of 50-50%. Think of half inverters, half synchronous machines. Okay, so you cannot sort of say there's no constraint. There's still constraints. This kind of system still puts a type of constraints on the controllers you can adopt. Okay. Yeah. Or we're trying to move to a case where we have more inverters. Right? The trend is we're going from at least sort of a relatively low amount of renewables to more renewables. And you look at things that they're going to 100% renewables, then most times they'll be interfaced with inverters. So that's actually a goal. But we won't get there for a few decades. So we're looking at the sort of intermediate stage of the system, or the transition stage of the system. Right, so we'll always have those times, but we'll be sort of much more dominant, right? We'll flip the current setting. So you have some hydro time. So to do this kind of design, we're facing a bunch of challenges. Because the challenges is, if you're an inverter, you only get your local measurement. You measure your local frequency. There's no explicit communication within the system. You measure your local frequency. You want to control a system that has nonlinear dynamics. We're focused on power flow equations. These are nonlinear equations. Right? So we're doing a local control of nonlinear systems. And then what do you want? Right? What you want is you want your control effort to be relatively small. You don't want to, you have an inverter, you have limited power output, you have limited energy. You want your control effort to be small. you also want your frequency deviation to be small. So you're basically trading off a control effort versus making the frequency deviation small and make sure the system eventually converges to equilibrium. Right, so we'll be a little bit clear about time scale, but here think of you have a perturbation, and then we look at the system for a long time until it settles down, and we want to bound the maximum deviation you can have. We want to bound for the infinity norm of this curve that you have. Think of short over seconds, 10 seconds. To think over this time scale. Okay, so this is our challenges, right? So. And our approach is we want to optimize controller. We're going to search for structure controllers. We're going to search for the right type of control function we should have on the inverters themselves. Okay. So the outline of this, we'll talk about how do you systematically think of how you should find control. We're going to do learning, but how should you think? Which kind of controller should you run? What we want is we want to guarantee system stability. Okay? We don't want to trade off optimality versus stability. The system should be stable. Then we can optimize performance on top of that. So we'll do a lossless system first. Then we'll look at the lossy system, so for simplicity. So by lossless, we mean if you look at this power flow equation, we'll assume that B is much larger than G, takes us sort of the standard assumption. And then we have only the sign term left over. So this is we'll first start with this sort of lossless equation, power flow equations. Then we'll circle back to the sort of more full AC power flow equation to look at this too. To look at how should we learn, but basically how stability and learning interface with each other. So I'm sure folks here have pretty much all seen this power flow equation. Just for some notations, we have an angle, frequency, right? So angle, the time derivative of the angle is frequency. Then this is the swing equation. So what we have is we have some inertia, some power injection. This is power flow. And our goal is to design this controller U. Our goal is think of you're a inverter. You measure your frequency, your local frequency. You have some feedback to power. So this function U is something you want to design. So local frequency. Sorry? They're on the grid side. So think of PLL measuring the grid side frequency. Yeah. So this is phase lock loop measuring the grid side frequency. So if you talk about linear droop design, you basically have this as a linear function. When you talk about inverters, your question you ask is, can it be some other function? Right. So as I said, I don't want linear functions. I want this to be a better function. So what is your goal? Right? So how do you measure better or worse? How do you think about optimality for this kind of function? So we're going to, right? So we're going to, the way to look at this, we have things on a graph. Some are inverters, some are traditional synchronous machines. They're all linked by this sort of nonlinear power flow. And you want these two things to happen. You want all this frequency to synchronize, let's say to 60 Hertz for US grid. And you want to minimize the control effort you have on this kind of thing. So optimality will be measured in terms of a trade-off like this. I want to minimize the frequency deviation, let's say from the nominal setting, plus the control effort you have. So this is a sum between the infinity norm and the two norm on control. Infinity norm on the frequency on the control, two norm on the control effort. Okay? So anything that minimizes, let's say, a weighted sum of these two terms, we think is optimal. Right? So optimal means this is small and this is small. Those two costs are small, that's optimal. Okay? So,
sorry, should we ask questions?
Yeah, you can ask questions. Yeah, go ahead.
I mean, why do you consider as, I mean, you say that your frequency will converge to the nominal value,
right?
So this is a discussion that I had with Maria. Like after was understood, this is a problem of primary frequency control.
Yeah, primary.
So after that, let's say in the Nordics or in European countries, frequency settles to the steady state, which is different from the nominal value.
Right.
So in that case, your second norm is you have to carefully design which time frame you choose because you have steady state frequency variation. It doesn't go to the nominal value. So here you assume that actually your inverter also play a role of secondary control and put back the frequency.
Yes, we'll restore the frequency.
So basically, then you are doing two functions. You're reducing the instantaneous frequency deviation, which is infinite norm in your case, and you're putting back frequency back.
Yeah.
All this process.
Yeah.
Okay, but how do you know that second norm will actually actually reflect the optimal performance?
Right. Okay. Yeah. So that's a good question. Right. That's a good question. So let me repeat the question for the audience on Zoom. So the question is, so those can be things of doing two things, right? We want the frequency deviation to be small. We also may want to recover the frequency back to the nominal, right? So that's doing two functions. The question is, why is the second norm a good cost, right? Why is the second norm a good cost? So second norm is cost if you think about things like, so this, if you think about storage, you can measure, this is the energy extracting from storage, so you can use second norm. There are better functions, and the thing I want to say is we don't need this to be a second. So think of this as an example. You can put in whatever function you want for the controller here. We don't require convexity on this cost function actually. Right? There's one nice thing about learning is we don't need this to be convex. So if there is cost function that's more economic, it makes more economic sense, you can put in that cost function. Okay. So think of this as a sort of example, because we want this is sort of the traditional thing people are doing control.
In control.
Yeah, but it's a good question. You can replace this by some other function if you want. Okay. So so the optimization problem becomes something like this. I have this cost I want to minimize, this sort of a trade-off between my system state and my control effort, subject to these physical equations, twin equations, subject to some limits on the my controller, right? My inverters have upper and lower bound, so they have constraints. And then subject to the case that the controller should not blow up your system. Okay, you don't want your controller to desplice the system, so you only look for stabilizing controllers. So this problem is you want to optimize over all static feedback controller U. Okay, so you want to optimize over U. This problem is sort of as non-convex as you want to be. There's nothing convex about this problem if you want to optimize over U. So it doesn't matter what your cost is actually. You can put in non-convex cost for this. Okay? Even if you restrict U to be a linear function, there's still not convex U. Okay, so even if you want to say, I want to search over the best linear controllers, it's still a hard problem to do. There's no good way to search over linear controllers. You know, if you want to do nonlinear controllers, this is a very hard problem to search over. So right now, if you look at our approach, okay, let's try learning. Okay, I don't know how to search over this. I do have this problem I can write down. I do know the physical equations. I can simulate this thing forward. So let me just do learning and see if learning learns a reasonable controller for me. Okay, let's just try this and see what happens. All right, so in our work, we'll also do learning. But the key thing of learning we want to do is we want to guarantee the learn controller is stable. So you don't blow up the system. We want to guarantee that this learn controller is robust to system topology changes. So you cannot assume you know everything about the system. You know the exact equilibrium. We want to make it fairly robust. And it turns out you can do this if you look at things like Lyapunov function passivity. The rest of the talk will walk through how do you look at stability from Lyapunov functions and passivity to come up with the right class of neural network-based controllers. Right? What is the right class you should search over when you do learning? But before doing this, we can ask the question of, do we need any of this math? Do I really need to look at Lyapunov functions? Why not just try the simplest things I can do? Parameterize things, control as a neural network, run RF. Let's see what happens in this case. So I know the power system. I can do time domain simulations. I can update the weights of this neural network controller and use very standard algorithms. So you can code this thing up in like a week or so. You can code this thing up and see what happens. And you try 39 bus, you run this, and you say, hey, this is pretty good, actually. My best neural network controller is a lot better than the best linear one I have. I do a lot better in training. So you're very happy with this performance. But the bad thing is you can, so give me one second. Bad thing is you can put this into testing and this sort of, you get some controller like this. Right? Who knows why this thing makes sense? But I'll tell you this is the best one I can get. Okay, so let's see what happens during testing. That's sort of the biggest difference between testing and training you can see. This thing does not generalize at all. Okay, you can train all you want. The training performance is quite good. When you actually put in system and do testing, this is where the system blows off. So that's why stability is important. You can, because the system is not linear, it's very large. Whenever doing learning, you only look at a finite number of trajectories. So there will be some perturbation that kicks your system in the wrong way, and it blows up, and you try to convince any system operator to use your controller, right? Just look at this, and they will never use your controller. Right? So naive learning is not very good. Right? So you don't want to naively learn any controller you want. Sorry? Oh, so there's a lot of buses, so they're just coding different buses in the system. Yeah, generators, right? So some are blowing up, some are not blowing up. That's for weird behaviors in the system. Okay. So, and the thing is, you don't see this kind of behavior in training. You actually cannot get rid of this if you don't restrict the structure of your controller. You don't see this during training. So, yeah. So you can think of, right, you run a system, you have a step input on a load, or you have a line fault, or you have any kind. So the disturbances are not necessarily large, actually. Yeah, not necessarily large. Yeah, they're not necessarily large. They're sort of similar to, let's say, a load you have on a bus. Right? They're not large. So again, this is why we emphasize stability. Right? This is unstable behavior. So if you look at this idea, is you cannot search over all controllers. Right? What RL does is let me search over every possible network. You really want to search over the controllers that does two things. One, I need to have an equilibrium at the end of the day, and I should converge to equilibrium. Right? So that's what stable controller means. Okay, those two conditions should be satisfied when you learn your controller. So the question is, how do you make these two statements into an algebraic constraint I can put on you? Okay, so that's our goal. Right? How do you get a computer to enforce these two things for you? Okay, so the question is, so if you look at this optimization problem, the question is, I have this constraint. You should be stabilizing. What do you do for the network? Because our goal is put this sort of a very global and general constraint to be something to have algebraic equations which I can work with. I can constrain the controller to satisfy that constraint. So how do we do that? Well, so this is where we have to look at Lyapunov functions. It's a nonlinear system, so let's first look at Lyapunov functions. So Lyapunov functions sort of measures the stability of the system by looking at the energy functions in the system. And very quickly, you have a dynamical system. You want a function v. Think of this as energy. And you want this to be positive when you're not at equilibrium. And you want the derivative to be smaller than zero. You want to decrease, right? So this means you want to dissipate energy until you get to the equilibrium. Then you stay at equilibrium. Okay, so this is, if you have this function, then the system is stable. Sure, right? So if this thing exists, everything goes to equilibrium. There's nowhere for the energy to go. Okay. Of course, the theory is nice. The question I always ask is, how do you find this Lyapunov function? Right? For linear systems, it's not too bad. You can find a Lyapunov function by solving a convex problem. For nonlinear system, you're basically on your own. Okay, so this is a very hard problem, typically for nonlinear systems, and searching for Lyapunov function. The good thing is we're not working with the arbitrary nonlinear system. We're working in the power systems, where folks have been looking at this function for decades, at least. Right? So what function do I have? Well, if you go back to the energy function for the Swain equations, this is a very well-known energy function. I'm sure Dan probably have seen this many times in his research. So this is, you can think of part of this is the kinetic energy you have in the system, this sort of frequency square, think of kinetic energy. The rest you can think of this as potential energy. So this is a sort of well-known Lyapunov energy function, goes back to at least 70s for the Praveen Maria's days. Goes back. Pi, okay, yeah, so it goes back to pi for this energy function. So this is not a quite true Lyapunov function. This thing is not lower bounded, but works for between angles from minus pi over 2 to pi over 5. This is good enough for our purposes. So we have this well-known Lyapunov function. So how does learning come? Right? So how does this help to us to learn a structured controller when we know this Lyapunov function? Well, so let's say we still want to use this function. Does it put any kind of useful constraints for us on the controllers? Okay, so let's look at it. So let's assume there's an equilibrium. So we'll prove this later, but let's say there's some equilibrium. When I put in this controller here, let's say there is equilibrium. So how do I make sure that the energy decreases when I go to this equilibrium? You basically write out the Lyapunov function with this U. Okay, so you go to your Lyapunov function, write out all those conditions with this U inside the dynamics of the system. One thing is you want this to be, basically you want this thing to be zero at equilibrium. This will tell you U at zero must be zero. Basically, the frequency is not changing, do nothing. This is a very simple, this is very intuitive idea. Then the dissipative factor, this V dot must be less than zero, turns out to give you this algebraic condition. Okay? You need to satisfy this condition for this Lyapunov function to have a decreasing energy, for the derivative to be negative. Okay? So at least we turn into stability constraints into some algebraic constraints that we can look at. And if you stare at these two equations, for a few minutes, you'll quickly realize this is actually a very simple constraint you can enforce. This is sort of a trivial form, right? So I want this thing to happen. You look at it for a while, well, these are the only class of function you get. Okay, what this says is, if shit goes to zero, okay, so this function has to cross the origin. And this says, well, this basically says your function is increasing. Okay, so you're larger than equilibrium, you have to be larger than equilibrium. This is smaller, this thing has to fall. Okay, so you have this is the class of functions you have. Okay, so we're changing a stability constraint into algebraic constraint by restricting your curves to be in this form. Okay, they have to be in this form for us to work. And turns out this will guarantee actually you will have equilibrium. So you can prove this later. Go ahead. Yeah, go ahead. So here is the positive slope. So if the frequency is very small, you still want to do sort of magnitude larger action. Right? Oh, so this the sign is the nominal minus the frequency. Yeah, so the sign is the nominal minus. Yeah. Yeah. So this, so there we can think of this as okay, right? So this is the functional form basically. Right? Don't do RL for arbitrary class of functions. Use RL to search over this class. Okay, so yeah, go ahead.
So
right.
You are guaranteeing to let's say satellite frequency.
Right. Yeah.
But there is no guarantee that you have anything to control the area dynamics or low frequency oscillations with the components in the transient, at least over some time scales. And that's what people worry about quite a bit now. So you're just concentrating on the driving frequency.
Right. So yeah. So the guarantee here. So let me repeat the question: is what happens during transient? This says you have equilibrium, but what happens when it gets to equilibrium? So we can control transient. Remember by changing the cost function. So remember we're trying to optimize the cost function. So if we add some transients related to cost into the cost function, and then we optimize that cost, this will deal with transient, or at least try to minimize transient. Yeah. Right. Yeah. Right.
So the problem is a little different because now you have these intermittent oscillations all the time.
Right. Yeah.
So the question is
right. Yeah. So yeah. So let's save that off, and then we can talk. Right. Yeah. Yeah. So let's save that off a little bit. So here, let's think. So this is the class of functions you want to optimize. So the theorem basically saying that if you give me this frequency dynamics, if your controller satisfies, the monotonic increasing function to the origin, you're guaranteed to reach it. There is a unique equilibrium in a pretty big region. You're guaranteed to reach it. The proof is actually not very hard. So I won't write the proof here, but the proof is quite quick. It doesn't take that long. So this monotonicity basically gives you there is a omega star, there is equilibrium. Lyapunov arguments tells you your energy has a decrease. Little bit thing is you have to use Lascelles principle to really get to the unique equilibrium. So that's the bit sort of non-trivial part of the proof we are used there. And then what we can do is we can bound the region of attraction. So we can tell you if you start within this region, for sure you'll reach the equilibrium. Okay, so that's a proof. And if you look at the controllers, basically what it says is linear is fine. Right? Let's go back to linear. What does linear work? Well, linear satisfies this condition. It's perfectly fine. And this sort of thing is also okay. We'll stabilize the system. This is not okay. Okay, this thing will not stabilize the system. This will try to blow it up. Okay, so that's why the RL, sort of the naive RL doesn't work. And so learn something like this. And it will blow up system. And you can clip the output, satisfy power constraints. You have constraints, you can do that. So what we've done to recap is we're taking a bunch of stabilizing constraints, we made it into an algebraic constraint on each of the local controllers. As long as each of the controllers satisfy our increasing and monotone property, we're guaranteed I can satisfy this constraint. Then I can use RL just to minimize this problem, right? With this cost function or whatever cost function you want, because I know the system will be stable. I don't have that. Yeah, go ahead.
So just to be clear with so
yeah.
Here are you trying to find the best slope for your inverter? No. What do you assume is your controller in your inverter base?
So your inverter can implement something that's not. So the question is, are we just optimizing over the slope? We're not, right? So we're allowing inverters to do something like this for many pieces.
I mean, usually, at least in areas where I work, this is a steady state curve. Is this a steady state?
Steady state curve. This is a static controller.
So what? How does it reflect some dynamics? What happens in between? Do you also, because if you're trying to reach the nominal frequency, you need some integrator that will do the job. You cannot just rely on the proportional gain. So where do we see the integrator part?
Oh, where do we see integrator part? Okay. Yeah, so that's a good question. So you can have this in a integrator loop. So you can put this in, so you can create another variable and take that to be an integral control. Yeah. Is that the case here? So you can put that in, okay, so for now, let's think of this as static controllers. Let's think of this static controllers.
Yeah,
right? Like this.
Static control, but
right.
How do you bring frequency to nominal? I mean, here in this case, when you just
yeah, in this case, it may not settle in where the frequency is nominal. Actually. It doesn't have to settle back. You can see yeah. Because, yeah.
So if you add the integral
yeah.
controller, it's really hard to go to those decimal stability gaps.
No, still works. Yeah, still works. Yeah, still works. It's not in this talk, but I can talk after. When you have integral control, this still works. Yeah, still works. That's the same constraint, actually. Okay. So, well, this kind of constraints, right? So you want this kind of, so the question is, if you have a neural network, how do you make sure the function is like this, right? So you have to put some constraint to the neural network to make sure you stay within this type of functions. Okay. So to do this, the way we do it is you break up this into two parts. So you think you have an increasing part, you have a positive part, you have a negative part. How to deal with one part is actually very easy from neural networks. Because let's think of you building a neural network, stacking up ReLU layers, or you have ReLU activation function. What's a ReLU? Right? ReLU is just this kind of thing. So how do you build something that goes across the origin and increasing? You just keep stacking ReLU pieces like this. Okay, so this is one line of code in your code. That will make sure you follow this type of curve. Okay, simply stack ReLUs up. Make sure your parameters are all positive, basically, then you're done. Okay, so this will actually, by design, enforce your controllers to be in this form. Okay, we don't need to do regularization, we don't need to do any of that. This is an explicit construction of the controllers in this form. Okay. Right, so let's see some simulations. So here we again take the 39 bus system, we add some inverter-based resources, and let's see what happens to the system. So here, to be clear, we're going to simulate with all the dynamics we can find. Okay, so this will have not just a classical second-order swing equation. We're going to put in this sort of sixth-order machine model. And to make sure we don't assume sort of too ideal of power electronics, we're going to put in the entire PIL into the simulation. Okay, so we're going to put everything in the simulation and see how it does. So it turns out, of course, your cost is much lower for the neural network-based one than the linear ones, as expected. You're essentially trying to minimize cost, it will do better. And then you have some controller which look like this. Okay, so this is the power limits. Then within the limits, it finds you a curve of that shape. Okay, so I don't know why this is optimal, but this satisfies our constraints. And turns out this type of controller will minimize cost. So the gold one is a linear controller. Okay? This is sort of the best linear slope you can have. This blue is whatever learned by whatever we learn from neural network. And neural network tells you this is the shape it wants to have to minimize. Yeah, so this is sort of weird looking, I don't know why it does this, but this is the thing you learn, right? This thing you learn. Yeah. Right, so the cost function is the old one we have, where you minimize the infinity norm on frequency deviation, plus a weighted term that's a control answer. Right, so this is for a particular choice of the weight on the cost. It's not linear, it's quadratic in the control effort, but it's the frequency part is the infinity norm. So it's not sort of convex in the controller. There's some, yeah. No, we don't need that assumption. So that's a cost we can find. That's where in the literature people use. But you can definitely replace that with any type of cost function you want. Right, we're going to use, right, so we're going to minimize this using bypropagation anyways. So whatever cost works equally well to the algorithm. The algorithm doesn't care what cost you have. It makes no assumption on cost. Yeah. Yeah. This is testing. This is testing it. Yeah. So everything is testing it. Yeah. No, we don't have the problem, right? Yeah. So that's a hope. Yeah, so this is testing this. Yeah. So this is again showing the time domain trace. Basically, we can do this neural network basically just has a much lower control answer. So there's in the paper, there's, yeah, go ahead. Mm-hmm.
I think we compare this without somehow testing every generator or every version control before you put it on the system, that it needs some interconnection stuff.
Right.
And those interconnection numbers are much more tricky.
Sure, yeah.
It keeps oscillating. They would say, okay, transient should not be bigger than something.
Right.
And it gets to central within 2 seconds.
Right, yeah.
I think that this choice of autonomous infinity norm, I think it's very critical. Is there a generalization here? If you were to have more,
sure. Yeah, so you can, yeah, so what you can do is you can put a, right, so the question is, okay, suppose you don't want to bound this infinity norm, but let's say you want to bound a 2 norm of frequency. Yeah,
I think you want to do it over short time.
Right, so here we cannot guarantee this will settle exactly in 2 seconds. What you can do is you can tune the cost on the frequency deviation large enough. Then we'll spend a lot of control effort to make sure this settles down quickly.
So one of our former is the photo here. She, like, if you choose the right exponent function, you can look at the exponent.
You can look at exponent, yeah, we can look at exponent,
so
yeah.
Probably a good way to,
yeah, so, right, yeah. Yeah, so this is also, we are also exponentially stable, but we don't tune the exponent. We don't tune the exponent, yeah. Yes, yeah, we can. Yeah, so you can estimate the exponent out of this, and you can think of that as part of your cost. You can write as a function of your control. You can relate to the slope. No, yeah, it won't be linear.
So that is, I think, I did the graph myself several times with saying some nominal control or something. Then you show it to them, and they say, "Well, it doesn't pass."
Right. Yeah. You can tune all this. You can tune all this. Yeah, you can tune all this code. Yeah. So here I want to show sort of robustness. The topology changes, right? So what often happens, you have this sort of planned and unplanned outages. Right? So let's say you train your controller for this nominal network. Then suddenly you have two unplanned outages that takes out 2 of your lots. And what happens to this? Well, so we're fairly robust to that, actually. So this is a pretty big step we put in here. It settles down after a while. Then you have a line outage here, then settles down pretty quickly. Okay, so this is when we're training the controllers, I did not see this line outage. Okay, so this is entirely in the testing setting. This is, yeah. Sure.
So what are the different lines?
Oh, so the different generators in this, right? Different color. We're showing different frequencies.
So when you have a step disturbance,
right?
Initially, some generators go above 1 hertz initially. After less than 1 second, some of them go below.
Yeah.
How you explain that? I mean, it seems like there is no PSS in the system. There is like, it's very weak.
Oh, we're putting a pretty large step disturbance actually.
I mean, this is a line. Yeah.
No, so you have a line fault here, right? So this is when we start the system. We're putting a huge step. Yeah.
All right. I mean, it seems so unusual. Usually, like frequencies will follow the center of inertia behavior. So you will see that after a step disturbance, like at least the propagation of all frequency will be in one direction, and they will be they will oscillate again.
Not necessarily, no. So that's depending on how you start the system and what kind of stuff you put in. Right? So for example, the way we create this is you have a step going up, let's say this bus. Right. You have step going down this bus. You have all this kind of things. And we want to see whether this will stabilize.
Step disturbance at the same time.
Yeah, for all the bus. Yeah, for all the bus.
But what's the rationale for that disturbance?
So we want to test whether this thing works, right? So we want to put in a very hard step for this thing to control.
But what would be like a real case scenario for this disturbance? Let's say, I mean, when I test, I trip the largest generator.
Sure.
And that's the largest power imbalance. Sure. And that's called N-1 criteria.
Sure, yeah.
But here it's, I don't know, N-6. That means that you have the disturbance at the same time in 6, 7 buses.
Sure, yeah. So, yeah.
I mean, that never happened.
I think the intermittent resources do that.
Yeah, I think the intermittent. Yeah, I think.
Yeah, but not to this extent.
Yeah, so it's okay. It's okay. So you want to stop small disturbance, we can do a small disturbance. But we'll look better than this. So we have a small disturbance will look better than this. So it works for larger disturbances. We want to test what limit it works, right? It works for small disturbance. And the really thing is for a line outage, it works without ever seeing this some sort of training data.
So one thing, another thing, teaching will be very interesting to share that more with you. But we can create on these 39 bus example situation where if the line connections are not weak,
right.
What to do the dynamics. So you can destabilize it.
Yeah, you can destabilize it.
So how do these different electrical distances show up when you have to train them? You don't train generator by generator.
No. You train the whole system together.
What do you train exactly? Sorry, you train all the
simultaneously, right? You simulate the system you look at the system trajectory. You look at your cost, you do by propagation to all the controllers at the same time. You update all your controllers at the same time. So we don't explicitly take into that. We just put the entire cost into training. We don't need to train one controller. That actually, I'll come back to that a little bit later. I'll come back to that later. Okay, so this is testing for robustness. The reason why you have robustness is you look at these two conditions. None of these depend on knowing the network topology or knowing where exactly this equilibrium is, actually. These are the same conditions, same algebraic conditions, no matter what kind of topology you have, no matter where omega star is. Right, so the good thing about this work is the optimality certainly depends on topology, but stability condition doesn't. Okay, you have the same exact conditions for every network. You don't need to, say design for a specific network or specific interconnection. This works for all of them.
But you get different slopes.
You got different slopes, yeah. So the optimality does, but here it doesn't. So to recap, we have this kind of structure, look at the optimal functions. This generalizes to other systems. For example, if you have this kind of x dot equals fx plus gx times u, then this fx squared, if that's the optimal function, then the same design works. The same design methodology works. Make sure it's your controller or sort of this kind of increasing function through the origin. Okay. But the interesting case is I've been talking to you is about a lossless system. but parallel systems are not lossless. They may have small losses, but definitely the loss is not zero. Okay? So if you look at power flow again, you have a lossy term in here. The problem with those energy functions, they're very brittle to this lossy term. You may think, well, if the losses are small, a lossy system is simply a perturbation around the lossless system. That's not how this Lyapunov function works. They rely on exact cancellation of this lossy, of all the terms. So if you have a very small loss term, then suddenly your Lyapunov function, there's no quote unquote easy energy functions anymore. And the question is, does your theory survive? Right? So we've been talking about the theory, you got a nice condition for the control and so on, but you don't want to be in the space of designing physics spherical calls, right? So it doesn't only work for this kind of very idealized setting. What happens when I have small losses? Right? So part of people thought, well, if my old Lyapunov function doesn't work, then maybe I should not use this old Lyapunov function anymore. Maybe I should learn Lyapunov function. I think probably some of these. And so, I have these conditions anyway, so I can parameterize the Lyapunov function using neural network, just trying to get these conditions. The challenge here is it's very, very hard to satisfy the thing you learn is actually a Lyapunov function. And how do you know these conditions work for every point in your region? It's infinite points you have to test. You may have to use something like SAS solvers. That does not scale, at least in our experience, scale well to anything beyond 4 buses, or it doesn't scale. SAS solver doesn't scale. A lot of times when you learn these things using learning, you're very much dependent on knowing where the equilibrium is. But as we saw, the whole point is we have renewables in the system. The equilibrium gets kicked around all the time. Right? So I want something that's sort of independent of knowing a specific equilibrium. Okay? So I want to extend our method to lossy cases and not to go through all of these. So how do we do that? Well, and the idea is I want something that's sort of gradual transition, not it works for lossless, completely falls apart for lossy. I want to think of, as losses, as we have more and more losses, it's harder and harder to control. We want this sort of more gradual transition, graceful transition. Works for a large range of equilibrium points, scales to larger systems. Yeah, turns out that that's not how the math works. Right, so here we'll think of making use of this sort of equilibrium independent passivity, this EIP idea. And what this allows you to do really give you the idea of being a very graceful transition. It's really, they're not, it's not a 0-1 thing anymore. So the idea with passivity is if you look at the system, think of you have some input going to the system, some output coming out of the system. What does passivity do? Okay? Passivity at a very high level is I need a large input to get a large output. There are mathematical definitions, but think of passivity this way. So what this says is, if this is passive, then as long as, to blow up the system, the input has to be large. So I can make the input small, then the system doesn't blow up. So the math definition is basically, you look at this following thing. Think of this term, this is always a positive term. Think of this as the energy I have, I build up in my system. This thing has to be upper bounded from the energy I put into the system. Okay, you want this is what passivity means, right? If I can have this bound, that means my system is passive. The good thing about passivity is it allows you to build a Lyapunov function for analyzing subsystems. Okay, that's what the trick is. If you can make sure every part is passive, you link them up together, you get a Lyapunov function. So for example, think of a 2-bus system, right? How do we break it up? Well, one bus with an angle and frequency dynamics, some transmission line, another bus with angle and frequency dynamics. So we can analyze this thing part by part. And then we're going to put things back together to construct a Lyapunov function to make sure this thing works, okay? So this boils down to, let's look at each component and their interconnection. And to look at components, let's look at the loss. Because losses come on the lines, and that's a part we want to deal with for this line. Okay, so let's look at this function. So our input to the line is the angle difference, and output is active power coming out of the line. Think of it this way. And this does not have dynamics, so it's called a memoryless system. And passivity is actually pretty easy. Again, you've come to this increasing idea. So the output is increasing in the input, then the system is strictly passive. That's all you need. Okay? So now you can draw, let's see why a lossless system is simple. Well, this is the curve from input to output. This thing is increasing from minus pi over 2 to pi over 2. Okay? So that's why the Lyapunov function we have from last time works for this range. They satisfy this passive criteria. Now, if you put in a lossy system, what happens? Your strange is range. Because instead of a sine curve, you have this cosine plus sine curve. So it's not going to be increasing from minus pi over 2 to pi over 2 anymore. You have a smaller range. But depending on the G and B in the system, you can explicitly bound the range where this curve is increasing. So as you add in more losses, you just get a smaller region. Okay? So our theory will work for the region where this curve is increasing. Depending on your loss, it'll just be a smaller region, but still works for the entire region. Okay? We don't have to check equilibrium by equilibrium. Directly check a region here. So this is again quite graceful transition. If losses are small, you recover this case. They're large, you squeeze it a bit more. Right? Yeah.
Actually, that reminds me of Kostya and the Long's work on the Lyapunov function family. It also requires that.
Right. Yeah. Yeah. So this comes up quite a bit. This kind of problem comes quite a bit. And then now you look at interconnections. So basically, you have buses which give you angles that goes into the lines, which determines power flow, goes back to the buses and drives the dynamic. So you have this kind of interconnection, right? So, and if you do some math, basically for stability, what you need is this interconnection matrix and your control effort, this damping, to satisfy this LM9, to satisfy this inequality. And why is lossless easy? Well, for lossless systems, this thing is satisfied trivially. So why do you satisfy this for lossless system trivially? Because for lossless systems, the power you send in from each end cancels. Sine is odd function. They cancel each other. So what that implies is your interconnection matrix is so-called skew symmetric. This M plus M transpose will be exactly 0. Then what does stabilize your system? Well, any non-trivial amount of control will stabilize your system. Okay, so for the lossless system, you just need some positive control effort. And you eventually will come back to equilibrium. Okay, so for lossless, that's the idea. If you have a lossy system, what happens is you no longer have this skew symmetry. When they add, they don't cancel. So now you have two parts in this interconnection. You have a skew symmetric part, that's nice. You have a sparse part that picks up this sort of summation of losses here. So you no longer have a trivial control effort, right? You don't have trivial control effort. So you actually have a lower bound on the control effort. You have to do sufficient amount of control for a lossy system for the system to be stable. The good thing is this is a convex stuff. It's a very easy bound to get. And again, this will degrade very gracefully to the lossless case. Okay, so this is not a 0-1 thing anymore. It's just basically you write down your system, depending how much loss you have, you write down this equation and check what control effort do you need. So basically what tells you for feasible controllers, you have a lossless system. You just make sure your controller lives in these two regions. That's the increasing function, lives in these two regions. Of a lossy system, what do you see? You need to be bounded away. You have to have sufficient amount of control effort. Yeah. But within this sort of two triangular regions, you have any function you want. So when you search over your, let's say we're using RL to build neural networks for these controllers, all you need to do is lower bound the slope of the ReLU functions. This is right. So the idea was, I guess the idea is, at least if you look at the equation, is for loss, those things cancel. There's no energy buildup. Yeah. So, right. So a little bit, yes, yeah. Right. So I mean, yeah. So you think resistors will be better for stability? Right. Yeah. Right. You may go on stable. Yeah, the same thing. Yeah, it's a very good paper. Yeah. Right. Right. So yeah. So that's a good. Yeah, anyway, so you can basically, depending on how lossy it is, you get this lower bound on your control effort. Again, engineer your controllers to stay within these two sectors, then you're fine. And then you're guaranteed. And again, the lower bounding is very easy to check. It's a convex problem, you can easily solve it. So we don't need to say learn the Lyapunov function or do any sort of SAS solvers, anything else. Right? So you solve one problem, you get lower bound. Okay. So this lower bounding the controllers. So for example, there's a case showing that if you don't have a lower bound, things go blow up. You can still train, things go blow up. You do need a lower bound for things to be stable. So we actually did some experiments. So this is Brian, my colleague's lab, Brian Johnson's lab. We're doing some tabletop experiments, cutting things up to make sure this works. So it works for this sort of small setup. There's not that many inverters. So Brian got more ambitious. We're starting to build a bigger setup, 100 bus 50 kilowatt system. There's some 100 something inverters here. Although this thing did trip the building breaker, but we need to be careful how we wire this thing. Right, so the tradition in UWCE is our old building caught fire. You got some power people. So we're continuing the tradition of destroying the building and building power things. Yeah. Right. Yeah, switching, yeah. No. So PDA, if you switch fast enough, you can get you don't have to do linear control. So pulse is right, but we can program to different. So you have an FPGA driving those controllers. So if you have FPGA, you can implement different ones, so you don't have to do linear control.
But then you're not because you can only switch it.
Right, yeah. So we're assuming, right. So that's why we want to do actual experiments. Right? There are on-model dynamics, especially at the 10 kilohertz level. Yeah, 10 kilohertz level. So that's why we want to do experiments here. So this works for small. We want to do it for a much larger system. Again, hopefully we can wire correctly and then do experiment on a larger system, not trip the building again. Right? So the 50 kilowatt system, very large. Anyway, so going to the last technical part is this approach, if you think about it, is centralized or decentralized? It's quite funny. It's centralized learning, as Maria said. We require all the trajectories to look at the cost and do backpropagation. The implementation is decentralized. Once you train it, you put it there and they sort of run on their own. You really want plug and play in some sense, right? Maybe don't even train centralizedly. Can we train decentralized as well and not worry about this? So there's a game theory interpretation to this. We need to plug and play, right? They're each playing a game. There's mostly quite a bit of negative results in general, telling you this cannot work. However, for power systems, for the grid, there's a lot of positive results. I won't talk about positive results here today, but turns out, again, because our physics is nuts, we can get positive results when we have this sort of plug and play, when people are playing this sort of dynamic games. Okay? And so this leads to my conclusion of, if you want to do learning, right, it's quite popular to do learning and control, especially in power. They can solve, open questions, can solve some hard questions. And including physics actually makes your life easier. It makes your life more interesting and makes your life easier. So you really want to push for the control theories as far as you can. Push learning as far as you can and meet somewhere in the middle. But don't think learning will solve problems for you. You actually want to solve problems for learning. And use it for what it's good for. Of course, there are a bunch of future directions, right? We did not look at reactive power. We completely ignore reactive power in this whole talk. We completely ignore so in simulation, we had the inverter dynamics, but in theory, we did not, right? So power electronics are not perfect devices. They have their own dynamics. So how do we account for those kind of model dynamics? And again, stability doesn't really imply hard constraint. So you have hard constraint in the region you have to stay in. The Lyapunov function doesn't exactly give you that. So how do you think about hard constraint classification? There are quite a bit of challenges that we have to look at. But again, the overall idea is, as long as you can combine, your control, your power system theory and learning, there's quite promising directions to go. With that, I'll conclude my talk and take any questions.
Quick question regarding the first part of your talk. I'm thrilled to see that you just need the two conditions to guarantee robustness, but I was also curious, do you need to introduce some assumption on the size of disturbance that you work with? to guarantee stability in the system?
Yes, yes. So that's a good question, right? So remember the energy function I showed? It's a local Lyapunov function. It only works for a certain region in the angle space. So the assumption is your disturbance cannot kick you outside that region. If it kicks you outside, there's nothing we can say about it. Yeah.
I was thinking about that, but maybe if you explicitly produce it, the size of disturbance,
right.
You can also trade off the conservative.
Yes, yes. There's a turtle front. So we actually did that. So there's a backup slide on that. So if you want to see, so there actually is this turtle front trade-off. As you trade off control effort versus disturbance. Yeah. Yes. Good question. Yeah. Yeah.
In the inverter control,
yes. So the question is, again, for audience on Zoom is, right here we ignored faster inverter dynamics. We basically assume those are much faster than swing equation dynamics. That may or may not be true. Right? So one thing we really want to look at is how well there's actually interface. So how it's worked out so far in simulation and testing, but really want to make at least the theory more robust.
So basically your training set is a set of contingency or is a set of just state vector from the
set of state vectors. So we don't have contingency. Yeah. There's some random state function disturbances when we try. Yeah.
By the way, all the system level performance this study, for example, here you have a local controller for generator. So when they interconnect together, their system performance, how do you ensure the most
so that's the Lyapunov function. Right? That's where the Lyapunov function comes.
Only under certain conditions.
Only under certain conditions.
So you have to really be honest.
Yeah. So we satisfy the condition for the Lyapunov function, then that guarantees stability when they're interconnected. Similar for passivity, you have the same story, right? If they satisfy the condition you laid out for each of the paths, and then connect together, they play nice.
So there's another thing, I don't know where Rupa is, but we'll meet her today. She worked a lot on even on reactive power and all these things. There is a lot of synergy there.
Yeah.
But the thing is, what we do in power systems, we model nodes like generators, inverters, dynamic components, but we usually assume at the time scale of internet transmission is static. Right? So there's some G and D.
Right.
Where we have moved as a group to say, for this fast phenomenon, you also have some time scale.
Right.
So you go from DAEs to ODEs.
Right.
And that changes completely the problem. And so then it depends on, like, you can even ask the question, like things that Daniel is interested in public system. If you control the impedance of the line with HVDC,
yeah. No,
things change up and down. So it's a very rich field for a lot of work for future. And so all these postdocs, all these guys are finishing. I think I wish I were as young as you guys. So for more than one reason. But I think we should finish the formal thing.
Do you have a question on Zoom? If you want to, I can answer.
Currently, there's no questions from Zoom, but I do have one last question.
Okay, sure.
So you use the Lyapunov function for the stability guarantee.
Sure.
And from my experience, it's kind of like when we did the optimal control, we realized that if your cost function is the integral with quite a long time horizon, then the stability seems to be guaranteed automatically. For example, like your cost function is just the infinity norm and also the two norm, but there's no integral.
Right. Yeah.
And my point is that if we take the integral quite long time horizon, then that cost function would force the system to converge.
So not in our case, right? So remember remember the training example I showed you, right?
Right.
All of those converge very nicely. If you have an integral cost, those will have very low cost, right? So in training, having integral cost does help the system to settle down. But then the whole question is during testing, you still may not get the right time control.
No, and just one clarification. I think what Dan is saying, you have to power open for instance, instead of meeting them path constraint, to throw them into integral of the performance function. And right, that's what you did. So we're talking about I think we need to.
Yeah, we can have further discussions.
Yeah, we'll further discussion. Yeah. So my point is, the thing is, in training, everything will look nice. You can put in whatever cost function you want, but solve penalty tend not to work when you do testing for this kind of system.
Like in the spirit of doing reinforcement learning, I think the learning approach to like the controller and the statement of the test set would be, well, what if we generate some adversary?
Right.
Did you explore any of that, or?
So that you require something like that. I think Tone did something like that, right? In one work is you basically look, okay, I have some function. For this set of points, it's a Lyapunov function satisfies these conditions. Can I find a new point that does not satisfy this condition, then add it into training? That process is very hard when system is large. Again, you want to do, again, you basically running SAS solvers at that point. It doesn't scale that well.
So, all right, so we should finish today, and thank you.